see here. All right. So where we leave off, we left off at the end of the last class, and we were predicting whether or not, let me go back here. We're predicting whether or not sodium Na2HPO4, so disodium hydrophosphate, was a acidic or a basic solution. And we had worked through and concluded that there were two different equations that we needed to look at. Right, we needed to look at both the acid and the base equation. So we had worked through, and we had our acid equation, and we then, from the acid equation, were able to look up the just simply the Ka from the table, and then for the base equation, we needed to calculate the Kb. So we did that. We had the table down below. We looked up H3PO4 because we realized that Ka1, Ka2, and Ka3 are all the relevant ones, the ionization constants that we were interested in. We then realized that for the acid dissociation constant, we wanted Ka3, which was 4.2 times 10 to the minus 13th. We calculated the Kb from the Ka2, right? And we had worked through deciding the fact that we needed Ka2 for that one, and we went through, plugged in the Ka times Kb equals Kw equation, solved for Kb, and came up with 1.6 times 10 to the minus 7. And we compared the two, the Ka3 versus the Kb, and we determined that the solution, because the Kb was larger than the Ka, was going to be a basic solution, and that's right where we left off. And so we, the point we're at is the sample problem. So if you take the time now to work through the sample problem, and I will share that slide right now. Okay, so let me share that. So we're on the sample problem here. All right. So here's the sample problem. And it says predict whether the dipotassium salt of citric acid, K2HC6H5O7, forms an acidic or basic solution in water. All right. So we need to work through and simply, obviously, figure out what the acid equation is, what the base equation is, and then you need to figure out which Kas and which Kbs we need to compare. So, right, you're looking at citric acid, right? We have citric acid right here. Right, we have citric acid right there. So you're going to figure out which Ka and which Kb are you going to use from here. So I'll give you a little bit of time to think about that, and then I'll give you some hints and clues along the way. So take some time to work through that. Let me see if there are any comments. Right. If you have any questions along the way, either unmute yourself and ask, or post it in the chat, and I will try to answer them if you're struggling to try to work through this problem. While you're doing it, I'm going to write it out myself. Alrighty, so post in the comments whether or not you think this is going to be an acid or a base. Acid or a base. Acids. All right, so when you're working through this sample problem, right, we're going to have two different equations. We have our first, which is going to be, the first one, which is K2 HC6. This is kind of too large. I need to, yeah. Okay. K2 HC6 H5O7 is in equilibrium with our H plus the K2 H K2 C6 H5O7 minus, and you simply look that up, and that's going to be our Ka3, right? So we have our Ka3, which is equal to 4.0 times 10 to the minus 7. Right, and then we have our base equation where we have the K2 HC6 H5O7 plus water is going to be in equilibrium with decay H2 C6 H5O7 because it's acting as a base here. Plus we end up getting hydroxide ions. And I'm going to put this in here, but we also have and form a potassium ion. We typically ignore it, right? Because this is just going to be one of our spectator ions, right? The spectator ion. So we're going to ignore the potassium ion, but it's floating around in there because you always wonder what happened to that potassium ion, right? And now, so what we need to do is we need to look in the table and figure out which acid, so this is the acid that we're looking at in the reverse direction, so we're going to be looking and analyzing our Ka2. So our Ka2 is 1.17 times 10 to the minus 5th, but we really want to solve for our Kb, and the Kb of this equation is just equal to the Kw, the 1.0 times 10 to the minus 14, all divided by the 1.7 times 10 to the minus 5th, which in the end gives us, after you do the math, 5.9 times 10 to the minus 10. So when you compare the two, you can see that our Ka is greater than our Kb, so therefore this is going to be an acidic solution, acting as an acid in solution. Is this making sense to everyone? So it's pretty straightforward as long as you realize that you're just doing, you're just using the equation, right, where we have Ka times Kb, Kb is equal to Kw, and you're able to understand. So the hardest part of this is being able to write the equations, right? How do we know what Ka to use? So you have, if you draw the, right, we look at citric acid right here. So if we look at the formula for citric acid, we're going to have our H3 C6 H5O7, right? This is going to be the one that's associated with Ka1, right? That's the first association. The second one, H2 C6 H5O7 minus, is going to be associated with our second association constant Ka2, right? Because now we've lost one of the protons. The third will be HC6 H5 H5O7 2 minus, and that's going to be associated with Ka3, right? And then the last, obviously, which no longer has a proton, is going to be our C6H5O7 3 minus, right? So this doesn't have an acid dissociation constant, right? Because it's no longer an acid. So when you're looking at your equations, you can see in the first one, we have the HC6H5O7. That's the one that's associated with the Ka3. So that's where you're choosing that from. The second example, when we're looking at the second example, the part on the left is the one that's acting as a base, right? Because we're drawing a base equation here. The one on the right is the one that's acting as the acid. And we can see that we have the H2, right? H2C6H5O7. So we need to use Ka2 in this example, in this part, because that's the one that's acting as an acid. And we're able to calculate the Kb. We can calculate the Kb of the conjugate base of this acid. And that's what this equation gives us the ability to calculate. So the Kb calculation here is, calculating the conjugate base, right, of this acid. Right? Let me change color, right? So we have the acid here, and this acid, we're calculating the conjugate base of it. And then so where's the point of the first equation you drew up with Ka3? That was to show you, this is we have the first substance is acting as both an acid and both as a base, because it's amphoteric, I'm sorry. And because it's acting as an acid or a base, we needed to figure out, when it's acting as an acid, what is the acidity when it's acting as an acid. When it acts as an acid, this is Ka3. Right? So we're going to be comparing this Ka3 down here to when it acts as a base in the second equation. And when it acts as a base in the second equation, the reason that we say it's acting as a base is because it produces hydroxide ions out in solution. Whereas in the first example, it's acting as an acid because it produces protons. So we're comparing the two equations, which is going to be larger, the Ka3 of the first equation or the Kb of the second equation. And since the Kb of the second equation is larger, smaller, we say it's going to act as an acid, because 10 to the minus 7th is larger than 10 to the minus 10. All right. Other questions on that? More questions? Going once? Twice? If not, I'm going to switch back to the slides. Freddie, you have a question? You unmuted yourself.
I don't have a question. I guess I accidentally clicked it.
Sorry, you broke up. I can't hear you if you're talking. Okay. Okay. Very good. All right. So now we're going to analyze what factors affect acid strength. So we're talking about, how strong an acid is. Obviously, we have, substances that, different properties that can affect what our acid strength is, right? We have the HA bond must be polarized with the partial positive charge on the hydrogen atom, right? And the partial negative charge has to be on the conjugate base side, right? And bond strength, right? When we look at bond strength, the weaker bonds can be broken more easily, making the acid stronger, right? So when we're talking, acid strength, the weaker the bond, the stronger the acid. And obviously, a lot of the bond strength is actually dependent on the stability of A minus, right? The conjugate base. How the stronger more stable that conjugate base is, the more stable that anion is, means you're going to have a stronger acid. So we've talked about some of these before. Let's just look at it from a simple binary acid approach, right? Binary acid consists of hydrogen and one other element. So what we're talking about is usually, just the simple substances. So we're looking at these simple substances in the little table off to the right, where you have hydrogen and one other element, even CH4, right? It's just combinations of carbon and hydrogen, ammonia, nitrogen, and hydrogen. So within a group, the HA bond strength is generally the most important factor. Oops, sorry. Trigger happy air. Right, so when we're talking within a group, right, vertically, in group 4, group 5, each of the individual groups, the bond strength is going to be the most important factor. And then within a period, the bond polarity is the most important factor determining acid strength. So when we're going across, right, the row, we're going to be talking about the bond polarity. So we're able to compare within groups and within periods rather easily. So if we look at the examples above, we have, if we're looking at group 7A, right? At group 7A, we have the acid strength, right? The HF bond, right? We're talking about the strength of that bond is the strongest with HF. Then it works its way down to weaker bonds. The same thing with water versus hydrogen sulfide versus hydrogen selenide. You end up increasing acid strength as you work your way down the periodic table, because the bond strength is decreasing as you go down the periodic table. And if you recall, you think about what this means. If you recall back many, many moons ago, when we talked about bond strength, right? Let's see, where am I? My pen's not working properly. Oops. Why isn't this working? There we go. All right, when we talked about, in particular, we had, the fluorine atom. Remember the fluorine atom, we looked at the fluorine atom, and we were talking, we had the, all of the electrons were in the, the outermost orbitals, the 2s and then the 2p, right? We had the 2p. And then we talked about bromine, and we had in the center the 2s and the 2p. But then we started having 3s and 3p orbitals. Right, so we have a 3s and our 3p orbitals. Our 3p orbitals are our outermost orbitals. And remember how we talked about that when you're moving down the periodic table, you end up with a more polarizable atom, right? The atom is more stable with a negative charge because that negative charge is able to be distributed around the atom more easily, right? So I'm sorry, this is chlorine, not bromine that I just drew here. I need to erase that. Right, this is chlorine in the center. My bad. Ah, come on. Technical difficulties. Right, chlorine, right? So as we move down the periodic table and then you go to bromine, you're going to have either 4s and the 4p electrons being the outermost. And so you have this polarizability, this ability to distribute the negative charge around a larger surface, which makes the atom more stable with a negative charge when we talked about ionic compounds. And that's the exact same argument that we can use here. When you're working within a group, vertically, and when you go from fluorine to bromine, you have a more stable substance, right? The same thing goes for oxygen, going from oxygen to sulfur, right? You're going from up in the orbitals, from the s orbitals to the 2s orbitals and 2p orbitals to the 3s, 3p's to the 4s and 4p's. So you end up more polarizable, more capable of stabilizing negative charge. Then when we look at the bases, right? So when we're ammonia, on the other hand, right, is going to be a very weak acid, extremely weak acid, because it's actually acting as a base. We'll talk about why in a second when we work across the period. But you can see as if we walk down the period, our Kb is decreasing significantly, right? Our Kb, so our basicity decreases significantly, which means conversely, because Kb times Ka equals Kw, that our Ka is going to be increasing. You can see we're seeing the same exact thing. It's increasing in acidity, even though it's not an acid. So you can see with carbon and silicon, they act as neither acids nor bases, because basically they're, the polarity of this CH and SH bond is very, very weak. So there's not really this desire to form an acid or a base, right? And that's what we're talking about when we work across the periods. Right? When we're working across the periods, we have our electronegativities. And do I have electronegativity? I don't have I have them in the future slides. I think I have some electronegativities. But when we're talking about our carbon-hydrogen bond, right? Our carbon-hydrogen bond, I believe carbon has an electronegativity of 2.3. Hydrogen is around 2.1. So, right, we don't really have, there's no dipole that exists here. We don't have a dipole that exists, whereas with HF, right, we have our HF bond down on the other end. Fluorine has an electronegativity of around 4.0, hydrogen around 2.1. So you can see we have a dipole that exists where there's a partial positive charge on one end and a partial negative charge on the other. So as you work your way across the periodic table, you increase the dipole, and as you increase the dipole, you're increasing its acidity. All right. Oh, sorry. Good question. The stronger the bond, the more basic or acidic it is. So it's the stronger the bond, the less acidic it is. The basicity has a few other properties that we'll have to talk about later. It's not exactly a bond strength thing. It has other reasons why something is more basic or less basic. Right. So oxyacids. So oxyacids consist of hydrogen, oxygen, and one other element. And that element you need to recognize is going to be a nonmetal. Right, so we're talking about a nonmetal here. Oh, come on, that. I'm having some serious lag going on here. Sorry. So we're talking about, we have our nonmetal. We've talked about, metals bonded to oxygen in the past. What we're talking about now specifically are nonmetals. All right. So generally, as the electronegativity of the nonmetal increases, the acidity increases for the acids with the same structure. So if we look down in the structures down below, right, we have our substance. So there's going to be the red red here is going to be, I don't know why it keeps popping up like that. So our red is going to be our oxygen. We have our OH, right? So we're looking at the acidity of this OH bond. And right, that OH is going to be forming the hydronium ion when we dissolve that acid in solution. And the green sphere here is going to be the not the nonmetal that we're talking about. So in our examples here, that green sphere, this is killing me. I don't know why this keeps popping up on me here whenever I click on the screen. I'm having some serious issues here. I apologize. I have some serious lag going on here with my computer. All right. All right. So when we're talking, we have our chlorine, bromine, and iodine atoms here. All right. And for whatever reason, I'm having technical problems here. I need to go to using my other pen. So we have our chlorine, bromine, and iodine atoms. And what we're talking about in regards to those, the chlorine has an electronegativity of 3.0. We compare it to bromine, 2.8, iodine, 2.5. So you can see as we're moving down the periodic table, the electronegativity is decreasing. We can even throw hydrogen in there for comparison with electronegativity of 2.1. And you can see what happens to the acidity, right? The acidities decrease as we move down the period. So as we have our electronegativity of the atom decrease, the acidity decreases. And if you think about why that is, what's going on, I can't show you something. I need to draw something and I can't. All right, everyone. I don't know what's going on, but I have some serious drag going with my computer. And hopefully it catches up in a second. All right. So if we look at our, I can't draw anything. Let me exit out of this program for a second and see if I share something else. All right. So if we look at our chlorine OH bond, all right, so remember we said how the strength of this OH bond determines whether or not we have a strong acid or a weak acid. And we also talked about whether or not what the strength of the partial positive and the partial negative charge is here. So obviously, I'm sorry, partial negative and partial positive goes the wrong way. Let me draw that backwards. The partial negative and our partial positive charges are here, right? So you can see we actually have, we're going to have a dipole, right? So if we have a dipole here, the ability of this chlorine atom, so this chlorine atom, because it's electronegative, can pull additional electrons away from the OH bond. So the stronger, the more electronegative that atom is, you get a larger overall dipole pulling electrons away from this OH bond, weakening this OH bond, which in essence creates a much smaller partial positive, I'm sorry, yeah, much larger, I'm sorry, partial positive charge here, right? And what that's doing is because you have an overall, larger partial positive, partial negative charge on the other side. right? So you have because you have two electronegative atoms, right? This is electronegative 2. You have two electronegative atoms pulling electrons away from that hydrogen atom. So you're increasing the size of this partial positive charge, weakening the OH bond more and more. So it's because the orbitals are the weaker bonds. So it's not more orbitals, it just has to do with just this overall stronger electronegativity pulling the electrons away from that oxygen-hydrogen bond, weakening the oxygen-hydrogen bond. So you have a much weaker oxygen-hydrogen bond, so that hydrogen is more acidic. You think of it from the perspective of if you have this chlorine-oxygen bond, you have very little electrons holding this oxygen and hydrogen together. You're basically removing electron density from this oxygen-hydrogen bond, so it's a lot easier for this hydrogen to dissociate and form a separate proton and keep the Cl O-, keep the negative charge and stabilize that negative charge on the other half of the molecule. All right. Let me go back to the presentation here and see if I can get it to work properly now. All right. So you can see in these examples, obviously, as you move down in the periodic table, your electronegativity is decreasing. As your electronegativity decreases, your acidity decreases because it's pulling less electron density away from that OH bond. Trying to. Let me see if I can. Let's see. All right. All right. I'm going to try closing my presentation, my PowerPoint, and then opening it back up again. Give me a second, because I don't know what's going on with it. It's not functioning properly. I'm having some technical problems over here. I'm trying to finish this up. Let me see if I can. All right, let's see what's going on here. All right. Chapter 16, where is it? It's not opening. Sorry, everyone. I don't know what's going on with my PowerPoint, but my file won't even open right now. So I'm trying to restart the PowerPoint. Seems to be starting now. It's coffee break time. Alrighty. I think we're there. Which is good because we're behind where we need to be. Right. Alrighty. So that's where we left off. All right. So we talk about oxyacids with the same other element, so we can compare, when that, non-metal, when it forms and has an interaction with, has bonds with more than one oxygen. We have multiple different oxyacids that can exist, and we'll see an example down below where if we go from the hypochlorous acid that we talked about in the last slide to chlorous acid, to chloric acid, to perchloric, we just keep increasing the number of oxygen atoms that are on the chlorine atom. So as we increase the number of oxygens on there, we're going to increase the acidity of the bond. So basically, they say another way of saying it, if the oxidation number, and you can go back to chapter 4 and review, oxidation number increases, the acidity increases. Right? If you think about what's going on, they're not drawing these, giving these justice. But when we're talking about, chlorous acid, we have, this can frequently be drawn as a double bond to an oxygen atom. Right, so it's a really bad double bond to an oxygen atom, but it can be drawn as a double bond to an oxygen atom. And when you deprotonate that's chlorine, not carbon. And when you deprotonate and make the conjugate base, you end up with a negative charge on that oxygen atom. And that negative charge can exist in resonance, where these electrons move inwards and displace and move the electrons outwards, so that you end up with the oxygen double bonded to the chlorine, with the oxygen on the on the other side. So you're able to distribute the negative charge that's produced on all of the different oxygen atoms. So thus, obviously, on chloric acid and then perchloric acid, you have the exact same result. And the reason for that, you're probably wondering, and you're looking at the chlorine atom is saying the chlorine atom has its octet. The reason that you're able to draw these types of double bonds is because we're actually using some of the d orbitals that are available, empty d orbitals that are close in energy, to make these what look like double bonds with the chlorine atom. So you're basically have increasing acid strength as we move from left to right. So the more oxygen atoms you add, the more stability there is. You can also think about it from the perspective that you have this dipole that exists here between the oxygen and the hydrogen. And then we have a bunch of other electronegative oxygens, right? There's a negative charge out here, a partial negative charge, lots of negative charges pulling a larger quantity of electron density away from that hydrogen atom. So the more electronegative the atoms there are, the stronger this dipole is, the weaker this OH bond gets. So you can see with hypochlorous acid, our Ka is at 3.0 times 10 to the minus 8. We get stronger by just simply adding one oxygen atom. We go up to 10 to the minus 2. And then from 10 to the minus 2, we essentially end up, and as soon as we add 2 additional oxygen atoms, we have an extremely strong acid, and perchloric is even stronger, right? So we have extremely strong acids that are completely dissociated. So here's a sample problem. It says arrange the compounds in each series in order of increasing acid strength. So take the time to work through this problem, and then we'll come back and discuss it. Here's the periodic table. I'm showing the electronegativities and down below. So use that to help figure out what the order of increasing acid strength is. So you have to think about what these atoms are and where they are in the periodic table when you're doing this. Actually, no, this is a sample exercise. I'm gonna work through it. I actually have a different one. Yeah, I'll work through this one first. I have a different one in the slides. All right. So the substances are binary compounds containing hydrogen, and they're and then in part B, they're all going to be oxyacids, which I didn't, unfortunately, I meant to cut that out. So for the binary acids, we're going to consider the electronegativities of arsenic, bromine, potassium, and selenium relative to the electronegativity of the hydrogen atom. The higher the electronegativity of these atoms, the higher partial positive charge on the hydrogen atom, so the more acidic the compound. So because potassium is on the left-hand side of the periodic table, right? So if we look at potassium, right, we have potassiums over here in the periodic table. With potassium on the left-hand side of the periodic table, it's very low electronegativity at 0.8. As a result, the hydrogen and potassium hydride actually carries a negative charge, right? Because if you look at the hydrogen atom has an electronegativity of 2.1, so it's more electronegative than potassium. So we actually have a KH bond with a partial positive charge on the potassium atom, not on the side of the hydrogen. So this is actually an H- equivalent. So it's going to be the least acidic of all of these substances, actually end up being the most basic. So arsenic and hydrogen have similar electronegativities. Right? You can look at them on the table here. Come on. So if you're looking at the arsenic, and so when you have electronegativities that are nearly identical, you're going to have a nonpolar bond, so it's actually not going to really be acidic or basic. And the electronegativity of selenium is 2.4 and bromine is 2.8. So the HBr bond is going to be the most polar of all of these bonds, and the hydrogen selenium bond is going to be next in line. So the HBr is going to be the most acidic, and then because it's more likely to donate a proton, whereas the hydrogen selenium bond will be next, and then then arsenic, and then the last potassium hydride, right? So if we're looking at the order down here, right? Here's the oxyacids on the next slide. So if we look at the oxyacids, you're going to consider both the electronegativities of the central atom and the number of oxygen atoms bonded to the central atom. So if we first look at the sulfuric acid and the selenic acid, you're going to have the same number of oxygen atoms for both. So since you have the same number of oxygen atoms for both, you're just simply going to be looking at the electronegativity of the high sulfur versus selenium. And in such cases, the acid strength increases with the electronegativity of the acid. And if we look at the table, we have our sulfur has an electronegativity of 2.5. Selenium has electronegativity of 2.4. So the sulfur you would expect to be a more electronegative, a stronger acid. So therefore, we predict sulfuric acid is the most acidic. For acids with the same central atom, the acidity is going to increase with the number of oxygen atoms bonded to the central atom. Right. So if we compare H2SeO4 versus H2SeO3, you're going to have H2SeO4 is going to be stronger than H2SeO3. Right. So if we're looking over here on the left-hand side, right? So the weakest is going to be the one with 3 oxygens. Then if you compare the two with 4 oxygens, the more electronegative sulfuric acid ends up being the strongest. All right, so there's a sample problem to work through. So if you take a second and work through the sample problem, those of you who don't have it, I'll pop it up on the screen. Here is it. All right, so here is the sample problem. What's going on here? There we go. So in each pair says choose the compound that gives the more acidic or less basic solution. So everyone take a second and work through each of these. Which one's most acidic, less acidic? So this one should be pretty straightforward. Hopefully by now you've seen that, right? If we have, as we work down the periodic table, we end up with more acidic when we have the substances that, because they're able to stabilize the negative charge on their own more. So the HBr is going to be stronger than HF. Now recognize this is different than the oxyacids, right? As the oxyacids, as you move down the periodic table, you're actually weakening, whereas with the substances that we're talking about here, right? There's my mouse not working. Right, when we're talking about the substances that are binary acids, right? The binary acids, they increase as you're able to stabilize the negative charge. Then we have in B, right, as we move from across the period, we're going to have H2S is more electronegative, so it's with the binary acid, the H2S is going to be more stable, so it's going to be more acidic. And then we have with the oxyacids, the more oxygens, the more acidic, so HNO3 is going to be the most acidic here. And the same thing goes when we look at here's the difference as we move to the more electronegative H2SO3, which is higher on the periodic table. Again, this is different than the HBr versus the HF. Right? So H2SO3 is going to be more acidic. Any questions on this part? So why is HBr more acidic? So as you move down in the periodic table, right? So if we have, the fluorine atom, right? Remember we talked about that when you have looking at the second orbital here, right? We have the 2s and the 2p orbitals that are here, where we have then you have the chlorine down below, and bromine below that. So you're talking bromine, we're all the way out to the 4s and 4p orbitals. Oops. 4s and 4p orbitals that are holding on to that negative charge. And that negative charge, so when you have that extra negative charge, it's going to be distributed over a larger surface area. So the bromine is what we talked about, what was called polarizability. And the bromine was more polarizable. This is back when we were talking about ionic compounds, probably, I don't know, chapter 5, 6, somewhere quite some time ago. And the bromine is more polarizable, so it's able to hold that negative charge, and it's more stable than the fluorine atom. And it has to do with the fact that you're just a much larger atom. You have much more surface area, many more orbitals to kind of distribute that negative charge. There's another question. Here, least to greatest on the board. So, I mean, when you're this, if we're looking at, let me share this. Right. The least to greatest is just like this here in the periodic table, Freddie. So when we're talking about least to greatest, we have our least to greatest is, right here, right? When we're working down the periodic table, and the strongest acids for the binary acids, the stronger is going to be down in the bottom right-hand corner of the periodic table, right? And we're pretty much talking about the only ones that are going to be acids are going to be in groups 6 and 7, right? As soon as we move to group 5, we move into becoming bases anyway. So you're talking about very few binary acids that are acidic, right? We have HBr, HI is down below it. So HI, HBr, HCl, HF, then hydrogen selenide and hydrogen sulfide. So as far as binary acids, it's a very small group that we're talking about. Hopefully that answers your question. And then even in regards to the oxyacids, there are very few oxyacids, right? We're talking about the oxyacids are going to be made from the nitrogen, phosphorus, sulfur, chlorine, bromine, iodine, selenium. So there are very few oxyacids that are going to be, we're talking about here as well. So it's a small group, of substances that we're talking about that make, that we're talking about here. All right, other questions before we go on? Trying to finish. We're pretty far, we're a slide or two, a class or two behind where we need to be with all of these delays. So carboxylic acids. So carboxylic acids are organic acids containing the COOH group. And the factors contributing to their acidic behavior are the other oxygen attached to the carbon, draws electron density from the OH bond, increasing its polarity, and its conjugate base, the carboxylate ion, has resonance forms to stabilize the anion. All right, so this is, if you think about this, this looks exactly like our other oxyanions, right? We have our oxyanions where we're going to have some group. I'm just going to draw it here. Right. Right. So our partial positive here, our partial negative charge there. And because we have an electronegative carbon-oxygen bond here, pulling electron density away, that increases the amount of electron density being pulled from here, which increases the overall electron density being pulled away from that hydrogen atom. Right, so we just basically are weakening this oxygen-hydrogen bond. And then when you form the negative charge, this negative charge is able to undergo resonance and distribute the negative charge on both of the oxygen atoms, right? So this electrons can bounce back and forth. So the carboxylic acids are a completely separate group of organic acids that we're interested in, right? Many carboxylic acids are, the reasons we have lots of different flavors in foods, the reason we have many different vitamins and minerals that exist are either, the minerals are frequently carried around as salts, the salt forms of these carboxylic acids. So lots of different carboxylic acids, vitamin C, and just to name one is one of the carboxylic acids that we talk about. Citric acid is out there. So quite a number of carboxylic acids. Right. So Lewis acid, Lewis base. So Lewis acid base chemistry. So Lewis acids are electron pair acceptors, whereas Lewis bases are electron pair donors. So when we talk about Lewis acids and Lewis bases, we're opening up the group of what we call acids and bases now to substances that are no longer just containing protons. So, when we talk about, so therefore, just like when we talked about, groupings where most everything was under the group of Bronsted-Lowry acids and bases for anything with a proton, all Bronsted-Lowry acids and bases are also going to be called Lewis acids and Lewis bases. There are compounds that do not meet the Bronsted-Lowry definition that will meet the Lewis acid-base definitions. So what does this mean? So if we compare ammonia's reaction with hydrogen and ammonia's reaction with BF3, right? So in this case, right, we have our, whatever the acid is, right? We have our, let's just say this came from HCl, right? The proton came from HCl, right? So this would be we'll call it our Bronsted-Lowry acid. Right, ammonia here is going to be our Bronsted-Lowry base, right? And then when the reaction occurs, right, the electrons react, and we form this new nitrogen-hydrogen bond with a positive charge. And the difference is when we talk about the Lewis acid and the Lewis base. So we have a Lewis acid and a Lewis base here, where we have the same lone pair attacks the boron, and the boron here is acting as this Lewis acid, and it forms this new nitrogen boron bond, and we technically should be drawing a positive charge here and a negative charge in the boron, and we end up with this substance now when we're talking about Lewis acids and Lewis bases, where anything that is able to donate lone pairs, right, donate these lone pairs to form this new bond is going to be considered a Lewis base. And any substance, in this case it's boron, that's able to accept that lone pair is going to be considered a Lewis acid. So yes, acids are going to accept electron pairs. So that's why a proton, right, a proton is accepting a set of lone pairs here. So it acts as this, Lewis acid, and just like the ammonia is acting as a base in both instances. In the first instance, we can call it a Bronsted-Lowry base. In the second instance, we're calling it a Lewis base because it's reacting with the Lewis acid. And unfortunately, I think I'm going to run out of time. I have run out of time. I got 1 minute left. I got a minute. So Lewis acid-base chemistry and hydrated metal cations. So the hydrated metal cations are primary examples of electron pair donor acceptor chemistry. The higher charges result in stronger water metal bonds, making them stronger acids. Right. So when we talked about, right, we had iron 3+ in the past, right, and that reacted with water, right. And we said that we had formed hydrates, right? What happens is this iron forms a hydrate. And you can see here what we did. And then we put a positive charge right here. So what we did was we donated electrons here. These electrons were a donated pair of electrons from the oxygen atom. So in this case, the iron 3+ was acting as a Lewis acid and the water was acting as a Lewis base. All right. So I'm going to pick up here, just to finish, I think this is actually the last slide, but I will speak about it for a couple seconds at the beginning of the next class, and then we'll start on with chapter 17. If anybody has any questions, otherwise, I think we're finished up. Thanks, everyone. See, did everybody else show up?